What is associativity and why is it so useful in parallel systems? By the end of this video, you should have 3 keys to make an operation associative. My name is Eric Normand, and I help people thrive with functional programming. So associativity is an important idea because it lets you easily break up a job, do the work separately in different threads, and then recombine the answers without any trouble. So I like to think of associativity as the essence of composition. So let's get into it. What is associativity? It's an algebraic property, meaning it's a characteristic of certain operations or functions. And what it really means is grouping doesn't matter. So grouping you can imagine as the parentheses in your mathematical expression, right? So I could have something like A plus B plus C with no parentheses. It's kind of ambiguous what the grouping is. But if I put parentheses, I could put parentheses around A plus B, or I could put parentheses around B plus C. Now we know with plus, it doesn't matter how I group it, which is why we leave out the parentheses, because it doesn't matter. But that doesn't matter is what associativity is. That's what that property that is naming. Another operation that programmers use all the time is string concatenation. Take 2 strings, join them together into one big string. This is an associative operation. Imagine you had 3 strings. Just to make it easy to explain, let's say you have the string with the letter A, a string with the letter B, and a string with the letter C. If I put and I'm going to concatenate them all together. If I put parentheses around A concatenated with B, and then I concatenate C onto that, versus putting parentheses around B concatenated with C and concatenate A on the front of that, you see I'm always going to get the same string at the end of the day. The string that I'm going to get is A, B, C. So that's why it's associative. So why am I even talking about this? It's a good question. Isn't associativity one of those math teacher things? I'm being a math teacher and teaching this thing that, is unimportant to everyday life. Well, it turns out that associativity is something we use all the time. We just take advantage of it and we don't even think about it. It's something we learned as kids, as babies, operating in the real world. It's just everywhere, and so we learned it, and so it's become second nature. We don't think about it, we just take it for granted. So associativity, why? It lets you break up a problem. Let's say the problem is too big. You want to break it down into smaller jobs that you can get help with, right? So you can call some friends over, and you're all working on the same problem, sub-problems, right? Or different sub-problems, and then lets you recombine them later. So let's say you had a lot of, you had a long document that you needed to proofread. Let's say you needed to read the document and cross out any words that you don't want to be in there. This is a simple operation, but it's 2,000 pages long, and it's due in 2 days. You just don't have time to do it. So you get some friends, and you take the stack of papers, and you divide them roughly. So let's say you got 3 friends. Now you divide it in 4. It's 3 friends plus you. You divide it into 4 roughly. Doesn't matter. And you just remember what order. You had the first stack, you had the second stack, you had the third stack, I'll take the last stack. And now you just work independently, crossing out those words. And then you put them back together in the same order, the work is done, right? It's associativity that lets you put the things back together, right? Just like a string. I could break I have a string with like 1,000 characters in it. I could break it up into multiple strings, and then later put them back together. That's what allows us to do that. Now, the order still matters, or it might still matter, right? In the case of this 1,000-page document, yes, the order still matters. You don't want the pages out of order. But we can all work independently, and when we put the answers back together, we should have the correct result. It doesn't matter how I break it up, right? I could give the first person, so we said is 1,000 pages among 4 people. I could break it up into exactly 500 pages each. 250 pages each. For 4 people, 1,000 pages total, so it's 250 each. Or I could be rough and give the first person 245 and the next person 255, and it's kind of not worth counting them. It takes just as long to count them as it does to do the work. So, but because it's arbitrary, I can break it up anywhere, and I know I can recombine it. Now, I know this seems like a silly property to go on and on about, but imagine if you had this property in some work that you had to do, right? Imagine you had some big task to do, and it might be too big to do on one machine or too slow to do on one machine. So you want to break it up. You want to use all your cores. You don't want to do just like the naive way of just starting on page 1 and going to page 2 and page 3 and just one at a time. You want to break it up. Not all things can be broken up and put back together. So having an associative operation that lets you recombine them together, recombine the answers together, is a requirement, and it's not guaranteed that that you have that. You have to make it that way. I like to think of associativity as the essential idea behind composition, where you take 2 things and you put them together and you make a new thing of the same type, right? This is composition, like at its most primitive, essential form. Just like you have 2 stacks of paper, you just put one on top of the other. You still have a stack of paper, but now it's combined, right? Same with 2 strings. Take 2 strings, combine them together, new string. It's the essence of combination, of composition. Okay, so I promised I'd give you 3 keys for making an operation associative. I hope I've made the case for why associative operations are really interesting. That the why I gave is for parallel work, but it also turns out that because they're the essence of composition, they're really nice for design, right? It means you can mentally, not just on your threads, right, but mentally break up the problem, and that means you could work on it recursively. It means you can kind of encapsulate and say, I'm just gonna focus on this part because it's actually hard to think of how to solve the whole problem, but I can break it down into something small enough to reason about in my head. So it's nice for design, and it turns out that a lot of things are much nicer if you have an associative operation. Okay, so how do you do it? 3 ways. Okay, so the 3 keys, really. The first thing you have to remember is that it is a binary operation. An associative operation is necessarily binary. Okay, if you have one that takes multiple arguments, like in Clojure and most Lisps, a plus will take 0, 1, 2, 3, or 4, etc. All infinite number of arguments, and plus is associative. So why is that? Well, it's because the grouping doesn't matter. So you could write out the grouping tree, the parentheses tree, and nest them and stuff, but it doesn't matter. So we just put them all in one level. But that's kind of a syntactic shortcut, right? Really, plus is a binary operation. Addition takes two numbers and returns a number. So when it's binary, the two arguments have to be of the same type, right? So like I said, plus takes two numbers, okay? String concatenation takes two strings. Another one is merging hash maps, takes two hash maps. So these are all associative. They take two arguments of the same type, and then they also return the same type. Okay, that's what lets you nest them arbitrarily, right? That's what lets you group them arbitrarily. That A plus B is going to give you the same kind of argument as C, so that you can combine it again using the same plus operation. That's the first key. Two arguments, same type, and the return type is the same type. All right. Number two, they have to use one way you could do it easily to make an operation associative is to use an existing associative operation on a data structure. So you use the data structure that already has an associative operation. So I've talked about, for instance, hash map merge. That's an associative operation. Try it yourself. You'll see that you can merge three things and group them arbitrarily. And if you build your data structure out of hash maps and you use merge as when you're defining your function, your operation, it will be naturally associative. All right, number three, and this is kind of a big one, and I hope I don't get too abstract with it. When you're giving work to your friends, let me give a little preface. When you're giving work to your friends, someone that you're who's working under you, so you're delegating work. What you want, the ideal, is to give them the entire job so that they can do it totally independently and not have to come ask you a million questions, right? Not to say, oh, do you have this thing? Do you have that thing? You want to be able to give them the work so that you can go do something else at the same time. You don't want to have to sit around and answer questions. Okay, so that same concept applies when you're dealing with associative operations, right? You want the string so you break this string up into two so that you can work on it separately. That string each string, both of them, they contain everything that you need for that work, right? So if you're counting, the letter A in this string, and it's too big to do in one pass, so you break it up into two, and now one thread is counting A's in the first string, and one is counting A's in the second string. That string has everything it needs. It knows its own length. It knows all the characters in it. So it's kind of silly to think about, like, of course it has everything it needs. But do your data structures, do your things have everything they need? Here's an example of a time when you don't have everything you need. So if you're calculating an average, often what people do is they have like a sum. The average is a sum over the count, right? So they have a sum and they loop through the array and add numbers into that sum, right? And then they get the count from the array and then they divide it. But notice you are doing these two things separately. You are summing separately from counting, right? What you want to do is have each value, each number in that array, be a self-contained value, a self-contained average, right? So this number, this array of numbers, think about it this way. If you took that array of numbers and you broke it up arbitrarily and said, okay, you average this part, I'll average this part, and then we'll combine them together. How can you do that? Because if the answer you get is an average of 7 numbers, and the average I get is an average of 8 numbers, it's not apparent how to combine those. Now, if you know that it's 7 and 8, then you can. But if you don't know, if you just know the number, you cannot safely combine those two averages. So what you need to do is, instead of dividing it out and getting the average, you bundle the sum and the count into, say, a new data structure. Let's call it just a tuple, because it's just a pair of numbers, right? It's a quotient. Eventually, you're going to divide them. But before you do that, you're going to leave it like this, as 2 separate numbers. So how do you do this? So instead of having an array of numbers, you map over that array and turn each one into an average. But it's an average of one number, so it's the number and a 1. So it's a tuple of the number and 1 of all of those numbers in that array. Now you can safely split up that array, hand one half over to your friend, you do the other half, and what do? You take 2 of these averages and you add the sum part, and you add the count part. Now you have a new tuple, right? So it's a combining operation. It takes a tuple, it takes 2 tuples and returns a tuple. So that's done. And now it's an associative operation. That means you can split it up over multiple threads safely, recombine them arbitrarily. There you go. That's something that I like doing a lot, is like squinting and thinking hard, like what are all the pieces of information I need in this value so that I can do this without having a variable over here that's got some magic or some partially completed calculation that I'm gonna use during the calculation. It's how we usually do it, but it's much better to move to the associative side. All right, so those are our 3 keys. So I'm just going to recap the whole thing. Associativity is an algebraic property where grouping doesn't matter. It lets you break up work, solve, get an answer, and then recombine the answers. I like to think of it as the essential of composition, the essential nature of composition, because of that idea. It's combining 2 things into a bigger thing. The 3 keys of how to do this: know that it's a binary operation, the 2 arguments are the same type, and the return is the same type as the arguments. You can use existing data structures with associative operations to build a new associative operation, and bundle the values together to make the work complete by itself. So I want you to do yourself a favor to learn this idea. Go find existing associative operations and the data structures they belong to. I'll give you some examples and just play with them in your own code to test whether they are associative. It's very easy to test if they're associative. If you can't do a plus b in parens plus c equals a plus b and c in parens, then it's not associative. So you got to find some way of making it not associative. All right. So string or array or list concatenation, these are all associative. Addition and multiplication are associative, but subtraction and division are not. Map merge, so merging 2 maps together. Function composition, so if you've got that in your language, give it a try. Function composition, if you compose 3 functions, it doesn't matter how you group them. and or on Booleans. Those are associative. And set union and set set union is associative, and set intersection is associative. Give that a try. Right. So test those out. Test those out in your languages. Right. So if you liked this video, if you liked what you've learned, if you found it useful, I would very much appreciate if other people could find this information useful too. So like, share, comment, and certainly subscribe, because then you'll get the next one, which I guarantee will be close in usefulness to this video, or this episode. So you'll get that one too. If you have any questions, if you want to discuss anything with me, if you want to suggest a topic for the next episode, please email me, eric@lispcast.com. You can also find me on Twitter. I love getting in discussions on Twitter at Eric Normand with a D. And look me up on LinkedIn and we'll connect up. Awesome. See you later.